Hello, I'm Colin Phillips.
And I'm Colin Jung. In this module, we will solve this second-order linear homogeneous constant coefficient differential equation in the specific case where the roots to the characteristic equation are complex.
There are three modules designed to help with the solution of this DE. This is the third in that series. If you have not watched the first two modules, we strongly recommend that you watch at least the first module before proceeding to this one.
Slide 1. Let's recap the story so far. In this module, we treat case 3 only, where both roots are complex. Recall that we use the constants a, b, and c from the differential equation to construct the discriminant, which is equal to b squared minus 4ac.
Depending on whether this combination turns out to be positive, 0, or negative, we get our three different cases. If the discriminant turns out to be negative, then the roots of the characteristic equation are complex. We call this case 3.
For case 3, we use the complex roots to form the general solution. For this case, the general solution may include, in general, an exponential function, along with the trigonometric functions sine and cosine. This is sometimes referred to as the trigonometric form of the general solution. We will also consider a special subcase of case 3, where the dp dt term of the differential equation is missing. And we will give an example of how to solve this case. Slide 2. Example of two complex roots. Consider the following second-order differential equation. This differential equation is chosen to satisfy the conditions of case 3. As usual, we will solve the question in two stages. Firstly, in steps 1 to 5, we will find the general solution to the differential equation. That is, we want to find the most general function p, which is a function of t, such that twice the second derivative of p is equal to negative 8 times the first derivative of p minus 26 times p, and that this is true for all values of t.
Then in the second stage, we will evaluate the arbitrary constants in the general solution to find the particular solution. To do this, we will need two conditions on p and t.
Step 1. Rearrange the differential equation into a standard form. This means that all the terms containing p are on the left-hand side, and that the order is second derivative, then first derivative, then p.
For our example, we must move the term containing the first derivative and the term containing p onto the left-hand side. We do this by adding 8 times dp dt and 26 times p to both sides. Here we make sure that the order on the left-hand side is second derivative, first derivative, then function p. Even though this is now in standard form, we can make the working much simpler by dividing both sides by 2.
Step 2. Write down the characteristic equation. To produce the characteristic equation, we replace d2p dt squared with k squared, dp dt with k, and p with 1. This gives us a quadratic equation in the variable k.
For our example, the characteristic equation is then k squared plus 4k plus 13 is equal to 0. Notice which derivative and which function goes to which term in the characteristic equation.
Step 3. Solve the characteristic equation.
We want to find the values of k such that k squared plus 4k plus 13 is equal to 0.
One way to do this is to use the quadratic formula.
The quadratic formula gives k is equal to negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 13, all divided by 2 times 1.
Recall that the expression under the square root sign, b squared minus 4ac, is called the discriminant. Now, if the discriminant is negative, then the solutions for k1 and k2 will include the square roots of a negative number. Some students may not have seen this before. Now, because the solutions include the square root of a negative number, we can no longer use just real numbers. To do this, we need to extend our working beyond real numbers and include complex numbers, which will be explained below. To proceed, we need to find k1 and k2 as some real number, alpha, plus or minus another real number, beta, times the square root of negative 1. The letter I is often used to denote the square root of negative 1. It is important to remember this because we will use it in the working below. We note that alpha is called the real part of the complex root, and beta, which is the coefficient of the square root of negative 1, or I, is called the imaginary part of the complex root. Using this notation then, beta will be a real number with no square root of minus 1 in it. In general, any number of the form a real number plus another real number times I is called a complex number.
For our example, the discriminant is 4 squared minus 4 times 1 times 13, which is equal to negative 36. So here, because the discriminant is negative, we get two complex roots for k. Here we will carefully explain how to simplify the right-hand side to get it into the form alpha plus or minus beta times I. The discriminant, negative 36, can be written as positive 36 times negative 1. Using the law that says the square root of a times b is equal to the square root of a times the square root of b, we can then write the square root of 36 times negative 1 as the square root of 36 times the square root of negative 1. Now the square root of 36 is 6. We then divide the whole of the numerator by 2. Thus k is equal to negative 2 plus or minus 3 times the square root of negative 1, where again the square root of negative 1 can also be written as I. Thus the two roots are negative 2 plus 3i and negative 2 minus 3i. We've now simplified the roots into the required form of a real number alpha plus or minus another real number beta times the square root of negative 1. Having simplified the roots of the characteristic equation to this form, we can now readily identify the real part alpha and imaginary part beta. Here alpha is negative 2 and beta is 3. Remember that beta is the real number 3, not 3i. We note here that factorising the characteristic equation by hand is difficult, and thus the quadratic formula is preferred.
Step 4. Use the roots to decide the case. As we have seen, if the discriminant is negative, we get two complex roots, where the square root of negative 1, that is, I, will appear. This corresponds to case 3 in our flowchart.
Here, because our roots k1 and k2 are negative 2 plus or minus 3i, and therefore complex, this example corresponds to case 3.
Step 5. Use the roots to the characteristic equation to write down the general solution. If the characteristic equation has complex roots, which is case 3, then the general solution can be written using both an exponential and sine and cosine functions. Here, the general solution is p of t is equal to a to the alpha t times c times cos of beta t plus d times sine of beta t.
Now remember to pay particular attention to the symbols inside the general solution. The coefficient of t inside the exponential is precisely the real part alpha of the complex roots. And the coefficient of t inside the sine and cos terms is precisely the imaginary part beta of the complex roots. Remember, c and d are the arbitrary constants. For our example, the roots are complex with real part negative 2 and imaginary part plus or minus 3. So alpha is equal to negative 2 and beta is equal to 3. Substituting these values of alpha and beta into the solution for case 3, we get p of t is equal to e to the negative 2 times c times cos of 3t plus d times sine of 3t.
At this stage, we have found the general solution to the differential equation. This represents the set of all the functions p of t that satisfies the differential equation. We will now find a particular solution, which not only solves the differential equation, but also satisfies the given conditions on p and t. To find a particular solution, we use the conditions on p and t to evaluate the arbitrary constants. Let's first interpret the conditions.
The first condition is p of 0 is equal to 2. This means that when t is equal to 0, p is equal to 2. The second condition is p of pi on 6 is equal to 3. This means that when t is equal to pi on 6, p is equal to 3.
Let us now substitute these conditions into the general solution to obtain equations for c and d.
Because the first condition says that when t is equal to 0, p is equal to 2, we use the general solution and substitute 0 for t wherever t occurs, and substitute 2 for p wherever p occurs. This gives us 2 is equal to e to the negative 2 times 0 times c cos of 3 times 0 plus d sine of 3 times 0. The right hand side then simplifies to e to the 0 times c cos of 0 plus d sine of 0. Now cos of 0 is equal to 1 and sine of 0 is equal to 0. So the right hand side simplifies to just c. So c is equal to 2. Now the second condition says that when t is equal to pi on 6, p is equal to 3. We substitute pi on 6 for t wherever it occurs, and substitute 3 for p wherever p occurs. This gives us 3 is equal to e to the negative 2 times pi on 6 times c cos of 3 times pi on 6 plus d sine of 3 times pi on 6. The right hand side then simplifies to e to the negative pi on 3 times c cos of pi on 2 plus d sine of pi on 2. Now cos of pi on 2 is equal to 0 and sine of pi on 2 is equal to 1. So the right hand side reduces to e to the negative pi on 3 times d. We now rearrange for d. First, using an index law, we can write the right hand side e to the negative pi on 3 as d on e to the positive pi on 3. We now multiply both sides by e to the pi on 3. So d is 3 e to the pi on 3. And so we have found that c is equal to 2 and d is equal to 3 e to the pi on 3.
Step 7. Having found values for the constants c and d, we can now write down our particular solution.
Here substituting c is equal to 2 and d is equal to 3 e to the pi on 3 into our general solution, we get p of t is equal to e to the negative 2t times 2 cos of 3t plus 3 e to the pi on 3 sine of 3t.
Slide 7. Example of a special subcase of case 3. We will now consider the special subcase of case 3 as we talked about in the first slide. For this special subcase of case 3, the discriminant is still negative, and so the roots of the characteristic equation will still be complex numbers. But here, b is equal to 0, and so the dp dt term is missing. We will now give an example of how to solve this case. Slide 8. Example of case 3, but where b is equal to 0. Consider the following second order differential equation. This differential equation is chosen to satisfy the conditions of case 3. However, observe that there is no term containing just the first derivative. That is, the coefficient b is 0. Now when b is equal to 0, the solution simplifies enough to treat this as a special case of case 3. As usual, we will solve the question in two stages. We will first find the general solution of the following DE. That is, we want to find the most general function p, which is a function of t, such that the second derivative of p plus just 4 times p is equal to 0. We will then find the particular solution using two conditions on p and t. Step 1. Rearrange the differential equation into a standard form. This means that all the terms containing p are on the left-hand side, and that the order is second derivative, then first derivative, which will be missing for this particular example, and then p.
Here our example is already in standard form.
Step 2. Write down the characteristic equation. To produce the characteristic equation, we replace d2p dt squared with k squared, dp dt, which will be missing, with k, and p with 1. This gives us a quadratic equation in the variable k.
So replacing d2p dt squared with k squared, we get k squared. Replacing dp dt with k, we get 0 times k. And replacing p with 1, we get 4. So the characteristic equation is then k squared plus 4 is equal to 0. Note that there is no k term because there is no dp/dt term in the dE. Note that a common mistake is to replace the p by k for this type of differential equation. Remember, we replace p by 1 when forming the characteristic equation.
Step 3. Solve the characteristic equation.
We want to find the values of k such that k squared plus 4 is equal to 0.
One way is to use the quadratic formula.
The quadratic formula gives k is equal to negative 0 plus or minus the square root of 0 squared minus 4 times 1 times 4, all divided by 2 times 1.
If the discriminant is negative, then as in the previous example, we will get two complex roots, and thus case 3. Recall that in case 3, the complex roots can be written as the real part alpha plus or minus the imaginary part beta times the square root of minus 1. However, the crucial difference here is when the dp/dt term is missing, then b will be 0. This means that when the dp/dt term is missing, and so b is equal to 0, then the real part of the complex roots will always turn out to be 0. Thus here, the complex roots k1 and k2 are just plus or minus beta I.
For our example, the discriminant is 0 squared minus 4 times 1 times 4, which is negative 16. Again, because the discriminant is negative, this means we will get two complex roots for k. Let's simplify the right-hand side to get it into the form alpha plus or minus beta I. Now the discriminant negative 16 can be written as positive 16 times negative 1. Again, using the law that says the square root of a times b is equal to the square root of a times the square root of b, we can then write the square root of 16 times negative 1 as the square root of 16 times the square root of negative 1. Now the square root of 16 is 4. We then divide top and bottom by 2. Thus k is equal to plus or minus 2 times the square root of negative 1. So the two roots are positive 2i and negative 2i. Having simplified the roots of the characteristic equation to 0 plus or minus 2i, we can now identify the real part alpha and the imaginary part beta. Here alpha is equal to 0 and beta is equal to 2. Let's observe again that because b is equal to 0, then the real part alpha is 0. We note that the roots could have been found much faster here by using simple algebra. Indeed, the equation k squared plus 4 is equal to 0 can be solved easily by just rearranging for k. Here we've used the quadratic formula to demonstrate that when b is equal to 0, the real part is 0 in the roots.
Step 4. Use the roots to decide the case. As we have seen, for this subcase, because the discriminant is negative and the dp/dt term is missing, then the roots are complex with real term 0.
Here, because our roots are complex with 0 real part, this is our subcase of case 3.
Step 5. Use the roots to the characteristic equation to write down the general solution. Remember, because the characteristic equation has complex roots, which is case 3, then the general solution may contain both exponential and sine and cosine functions. Now, because the coefficient of t inside the exponential is precisely the real part of the roots, and here the real part is 0, then the general solution is p of t is equal to e to the 0 times t times c cos of beta t plus d sine of beta t, which simplifies to just the cos and sine terms only.
In summary, when the derivative term dp dt is missing from the dE in case 3, we get simply that the general solution has only cos and sine terms. For our example, the roots are just 0 plus or minus 2i. So alpha is equal to 0 and beta is equal to 2. Thus, just substituting beta into our special form for case 3, where the exponential is no longer needed, we get p of t is equal to just c times cos of 2t plus d times sine of 2t.
This is the general solution to the differential equation. We will now proceed to find the particular solution, which not only solves the differential equation, but also satisfies our given conditions on p and t. Step 6. To find a particular solution, we use the conditions on p and t to evaluate the arbitrary constants. Let's first interpret the conditions.
The first condition is p of 0 is equal to 3. This means that when t is equal to 0, p is equal to 3. The second condition is that p dashed of 0 is equal to 4. This means that when t is equal to 0, the derivative dp dt is equal to 4.
Because the second condition tells us the derivative of p at t equals 0, we need to differentiate p to use this condition.
Using the chain rule on each of the cosine and sine functions in the general solution gives us dp dt is equal to negative 2c sine of 2t plus 2d cos of 2t.
We now substitute these conditions into the general solution and its derivative to obtain equations for c and d.
Because the first condition says that when t is equal to 0, p is equal to 3, we use the general solution and substitute 0 for t wherever t occurs, and substitute 3 for p wherever p occurs. This gives us 3 is equal to c cos of 2 times 0 plus d sine of 2 times 0. Now cos of 0 is equal to 1, and sine of 0 is equal to 0. So the right-hand side simplifies to just c. So c is equal to 3. Now recall that the second condition says that when t is equal to 0, the derivative dp dt is equal to 4. Therefore, using the derivative of the general solution, we substitute 0 for t wherever t occurs, and substitute 4 for dp dt wherever dp dt occurs. This gives us 4 is equal to negative 2c sine of 2 times 0 plus 2d cos of 2 times 0. Now sine of 0 is equal to 0 and cos of 0 is equal to 1. So the right-hand side reduces to just 2d. Dividing both sides by 2, we get d is equal to 2. Thus we have found that c is equal to 3 and d is equal to 2.
Step 7. Having found values for the constants c and d, we can now write down our particular solution.
Here, substituting c is equal to 3 and d is equal to 2 into the general solution, we get p of t is equal to 3 cos of 2t plus 2 sine of 2t.
Slide 13. Derivation of the characteristic equation. In this slide, we show why we use the characteristic equation to solve our second order DEs. To do this, let's consider the differential equation d2p dt squared minus 5 times dp dt plus 6p is equal to 0. Early in this series of modules, we show that e to the 2t solve this dE by substituting this function and its first and second derivatives into the differential equation and verifying that e to the 2t is indeed a particular solution.
Importantly, when we differentiate e to the 2t, this just produces 2 times e to the 2t. In fact, every time we differentiate e to the 2t, we multiply the answer by 2. So by trying a function like e to the 2t, we know that every derivative will just produce a multiple of the original function, that is, e to the 2t. For this example, when we substitute e to the 2t and its derivatives into the dE, the second derivative is 4e to the 2t. Minus 5 times the first derivative gives us 5 times 2e to the 2t, plus 6 times p, which gives us 6 times e to the 2t. This simplifies to 4e to the 2t minus 10e to the 2t plus 6e to the 2t. Importantly, because the special combination of 4 minus 10 plus 6 equals 0, these exponential terms therefore add up to 0. It's important to note that it is the 2 in the power that makes this special combination add up to 0. This idea is at the heart of all of our solutions.
It also turns out that if we substitute e to the 3t and its derivatives into the dE, we get yet another special combination of e to the 3t that adds up to 0, which means e to the 3t is another particular solution.
To move on then, we need to ask the question, what is special about the 2 and 3 in the powers of e to the 2t and e to the 3t that produces these special combinations that add up to 0 in each case, and thus means that these functions are solutions to the differential equation?
The answer to this question lies in the characteristic equation, which we shall now formally derive for this particular second order differential equation.
Because we have seen above that e to the 2t and e to the 3t solve the dE, let's investigate what happens if we try the function p of t is equal to e to the kt in our differential equation and see what this means for the values of k. To substitute e to the kt into the dE, we will need its first and second derivatives. The derivative of e to the kt is k e to the kt. If we differentiate this again, we get k squared times e to the kt. Observe that each differentiation of e to the kt produces just an extra factor of k. We replace the second derivative d2p dt squared with k squared e to the kt, dp dt with k e to the kt, and p with e to the kt.
And so we get k squared e to the kt minus 5k e to the kt plus 6e to the kt. Now we take out the common factor of e to the kt to get k squared minus 5k plus 6 times e to the kt.
Remember, we have substituted p of t is equal to e to the kt into the left-hand side of the differential equation. Now, if the left-hand side turns out to be 0, then this p of t will be a solution to the differential equation. So for this p of t to solve the dE, then either the quadratic or e to the kt must be 0.
Now, the function e to the kt is never 0. The fact that the graph of e to the kt never touches the horizontal axis demonstrates that this function is never 0. So the only way that p of t is equal to e to the kt is a solution to the dE is if we can find values of k that make the special combination k squared minus 5k plus 6 is equal to 0.
For this reason then, this special quadratic is given its own name of the characteristic equation. From our example above, we can now see more clearly why we tried the function e to the kt in our differential equation. We can see that 6p just produces 6e to the kt. We can also see that negative 5 dp dt just produces negative 5 times ke to the kt. And finally, d2p dt squared just produces k squared e to the kt.
So if we substitute p of t is equal to e to the kt into any of our second order differential equations, we will always get a quadratic times e to the kt. Again, if the quadratic is 0, then p of t will satisfy the dE. The most important concept in these modules is that if we can find a value of k that satisfies the characteristic equation, then p of t is equal to e to the kt will be a solution to the differential equation.
Moving on, when we solve the characteristic equation here, we get k is equal to 2 and k is equal to 3. So from the working above, we know that p of t is equal to e to the 2t will be a solution of the dE, and the same holds for p of t is equal to e to the 3t.
Let's now combine a few ideas we've seen throughout these modules and also show you how you might derive the general solution.
Earlier we said that if a differential equation is linear, then we can take any multiple of any solution and add it to any multiple of any other independent solution, and the result will also be a solution. Now, because this dE is linear, this means that we can add any multiple of e to the 2t to any multiple of e to the 3t, and this will also be a solution. So for this differential equation, the function p of t is equal to a e to the 2t plus b e to the 3t, where a and b are arbitrary constants, is again a solution to the differential equation.
Now, you may be wondering, how do we know for sure that this is indeed the most general solution? That is, how do we know that there are no other solutions that we've left out? Here, we have found a function that solves the dE, that is, an arbitrary constant times an exponential solution, plus another arbitrary constant times a different exponential solution. These two exponential functions are independent because they are not multiples of each other. A very powerful theory tells us that if we can combine any two independent solutions in this way, where there are two arbitrary constants, then it must be the most general solution to the second order differential equation in this module.
For those that are curious, this theory that is beyond the scope of this module is called the general existence and uniqueness theorem. From this theory we know that ae to the 2t plus be to the 3t with two arbitrary constants is indeed the most general solution to this specific second order DE, and importantly there are no others. So we have found not just a few solutions but every solution. This theory is not limited to the specific example we considered above. More generally, this same theory can be applied to every one of the cases we've considered in these modules. That is, this same theory allows us to construct the most general solution for every example of every one of the cases discussed here.
Slide 15. Getting from case 1 to case 3. In this slide, we will show how case 3 is really just a special instance of case 1, where the roots are complex. This is an advanced optional topic designed for curious and inquisitive students.
In the examples we have considered directly above, and in Module 1, when the roots to the characteristic equation were real and different, we used the form of the general solution for case 1. In that case, we use the real and different roots to form the powers of the exponentials in the general solution.
Above, for case 3, we saw that we used the complex roots in the trigonometric form of the solution. But now, we will instead use the complex roots of the characteristic equation in the powers of the exponentials. Let us proceed. We will now substitute the complex roots k1 and k2 into the general solution for case 1. Specifically, let the root k1 be the real part alpha minus I times the imaginary part beta, and let k2 be alpha plus I times beta. Substituting k1 and k2 into the general solution for case 1, we get the following.
We can then use the exponential law that e to the m plus n is equal to e to the m times e to the n.
Since e to the alpha t is common to both terms, we take it out as a common factor.
We will now use a pivotal formula that, quite surprisingly, relates the exponential function to sine and cos through complex numbers. This elegant relationship is called Euler's identity.
The formula states that for any value theta, e to the I theta is equal to cos theta plus I sine theta. This is indeed the critical step where the form of the solution is transformed from exponential functions in case 1 to the sine and cos functions in case 3.
Using Euler's identity then, we can transform the exponential e to the negative I beta t into the following cos and sine functions, and the exponential e to the positive I beta t into the following cos and sine functions.
Now recall that cosine is an even function. This means that the cos of negative x is equal to cos of positive x for all x. So we can rewrite cos of negative beta t as cos of positive beta t. Also, sine is an odd function. This means that the sine of negative x is equal to negative sine of x for all x. That is, for sine of x, you can think of the negative inside the brackets as moving to the front of the sine function. So using this, sine of negative beta t is equal to negative sine beta t.
We then expand both brackets. Finally, we group together the cos terms, where we have taken out cos as a factor, leaving a plus b times cos of beta t. Similarly, we group together the sine terms, where we have taken out sine as a factor, leaving I times b minus a times sine of beta t.
We now rename the constant a plus b and call all of it c. Similarly, we rename the constant I times b minus a and call all of this d. The result of this last step is that the solution is in the form of case 3. Thus we have shown that case 3 is a special case of case 1, where we relax the condition that the roots of the characteristic equation must be real and allow the roots to be complex. So because case 3 is just a special instance of case 1, then we could use just the two distinct cases 1 and 2 and still get all possible solutions.
But because transforming from case 1 to case 3 is a lot of work, it is much easier to go straight to case 3. In fact, if you are ever given a problem where the roots are fully complex, go straight to case 3, just like in the examples considered in this module, unless you're specifically asked to derive case 3 from case 1, as we have here.
In our 3 modules, we have shown how to find the general solution of this differential equation. In particular, we have concentrated on identifying 3 different important cases for the solution.
To do this, we have used the discriminant of the characteristic equation to decide which case to use. For this reason, it's important to understand and remember the flowchart that we have used to decide the case. For each of our examples, we have used the quadratic formula to solve the characteristic equation. We do this because it's easy to see the discriminant b squared minus 4ac in the quadratic formula, but it may be much easier to solve the characteristic equation by hand, and you should practice doing this.
You may sometimes be required to use the differential equation to find the general solution, and then go on to use 2 boundary conditions to find a particular solution.
Even though learning the flowchart and finding the general solution can be very systematic, finding a particular solution can be much more work.
For this reason, it's important to not only understand how to use our flowchart, but also learn how to use the boundary conditions to evaluate the arbitrary constants to find the particular solution. This is because you may need to use simultaneous equations and tricky algebra to evaluate these arbitrary constants.
In the beginning of the first module in this series, we explained what it meant for a differential equation to be second order, linear, homogeneous, and have constant coefficients. In this way, we showed that these differential equations are very specialized. It's important to understand that the algorithms we used in the examples here were geared to just this special class of differential equations.
Even though you can solve these differential equations by just using the methods and algorithms demonstrated in these modules, it is important to understand how specialized these DEs really are, how specialized these methods are, and also how many other types of DEs and methods there are out there.
In short, we've only fried some small fish, but it's important to appreciate how small a fish they are and how many more bigger fish there are out there.
This concludes the series of modules on how to solve second-order linear homogeneous differential equations with constant coefficients.